Today's content is probably the most important content, perhaps, for the rest of the semester today. So do your best to get yourself revved up and ready to go. The homework, once again, due next Tuesday, is pretty long. So you also want to make sure you're not waiting until Monday night or Tuesday morning to get started on it. And I think, again, as I mentioned before, if you can kind of do the homework slowly, that's probably best for your learning, to not try to finish it necessarily right away, especially the Thursday to Tuesday, but to do a little bit on Thursday night, maybe a little bit Friday morning, something like that, a little bit over the weekend, a little bit Monday, because that is going to help you retain information better, help you just remember it better, and so it doesn't seem so foreign when you come back the next Tuesday. So yeah, really important day today, and it's a shame some people are not here right now because I want to start more on time. This is a message for you guys. I'm probably going to put this video up for everybody on YouTube, and parts that are difficult, you're going to maybe want to rewatch, okay? In the PowerPoint itself, I've got various things that I'm not really going to spend much time on here, but they are here just in case you're interested. This page here is a derivation of the distribution of z squared. That's problem 45 in chapter 7. I actually did this in class 7 or 9 days ago, last week sometime. Not using the fingerprint theorem, but instead using deriving the CDF of z squared by differentiation, essentially. Well, by doing an integral, and then deriving the PDF by differentiation and seeing that the PDF for z squared is the same as a chi-squared PDF. So the point, again, is that if you square a standard normal random variable, you get a chi-squared random variable with 1 degree of freedom. This slide has a derivation of the left and right endpoints of the confidence interval to estimate a population variance. Did you catch every single word that I said there? Every single word I said is important and is something to kind of get into your heart and soul. With confidence intervals, you're trying to estimate population parameters, right? These are numbers that only God knows, typically, and we're trying to estimate them with sample statistics. That's what statistical inference is all about. Taking random samples, getting information from the sample, and then based on that information, saying something about the wider population and being confident in what you're saying about the wider population. It's like inductive logic. You're taking specific cases and you're generalizing. That's the method of science. It's not really so much the method of math. But we do math to derive these things. And the idea is you're trying to figure out before the fact an interval, one interval, there could be more than one such interval, that has a, for example, 95% chance of containing the population parameter of interest before the fact, before you actually do the sampling. The randomness is before the fact. When you say something has a probability of something like 0.95, it's a prediction about what's about to happen. After you've actually sampled and got the data, computed your sample statistics, and gotten a confidence interval, technically speaking, there's no more randomness involved. The parameter's either in the interval or not. And so Dr. Wetzel always used to say, there's no probability involved anymore. The 95% confidence level is just that. It's a confidence level. It's not really a probability anymore. I'm 95% confident, pretty sure that the parameter is in there. Now, that seems like maybe it's not a distinction worth making. I'm confident in it, 95% confident, but I'm not saying the probability that it's in there is 95%. And I would agree. Perhaps not a distinction worth making, but people do make it. As far as, if somebody did know the parameter value and you were making bets, I'm not advocating betting, and there was a 95% confident interval, you would make a bet based on essentially thinking of the probability of it being in there as 95%. Okay, you'd bet money on it. You'd be pretty sure. But again, nobody but God typically knows the parameter value, and so nobody but God typically knows whether your interval contains the true parameter value or not. Anyway, with all that said, all important stuff, this is just a mathematical derivation of those endpoints, okay? Based on a probability statement here, we want the probability that this this random variable here, n minus 1 s squared over sigma squared, who's, by a theorem, we know the distribution of this thing is chi squared with n minus 1 degrees of freedom, and so we can relate it to chi squared endpoints. And we essentially do some algebra to solve those inequalities for sigma squared, the parameter of interest, the population variance. You do want to write this interval, if you write it as an interval, in interval notation, left endpoint, right endpoint. You don't want to write it in plus or minus notation in this case, because the value of s squared, the sample variance, is not at the center of the interval. These are not equidistant from s squared, unlike a confidence interval for the mean being centered at x bar. Okay, so all important things to think about. Continuing to go quickly over some other slides that you can think about details if you want. This is officially the definition of a t-distribution. A t-random variable is any random variable that can be written as a ratio of a standard normal random variable, a z, to a square root of a chi-square random variable divided by its degrees of freedom. And when you can write such a thing, you say this random variable follows a t-distribution with gamma degrees of freedom. Historically, it's kind of an interesting story with the t-distribution. It was discovered by somebody named Gossett, and that's an amazing coincidence since we're at Bethel, and Nathan Gossett is here, and Eric Gossett was here, and he's retired now. Although the Gossett that discovered the t-distribution is spelled differently, with just one t at the end instead of two t's at the end, so they're not related. And these are sometimes called, as you see in quotes there, student t-distributions, or students t-distributions. Why? Well, Gossett, the person who first discovered the t-distributions, worked, I think, for a brewery and was using statistical methods for the brewery and discovered this method and wanted to publish it, but didn't want his employer to know who he was. So he published it as student. That was the name of what he published it under, so that the employer wouldn't know that it was him and want to fire him for revealing secrets that only they might want to know. So that's the little story behind it. So sometimes it's called students t-distribution. There is a typo in the text that I'm referring to here too, as far as the PDF goes. Lots of typos in this text. This one I'm highlighting. This formula is slightly different than what's shown in the text, and the one in the PowerPoint here is the correct one, not the one in the text. See if I can compare them here. Yeah, here's the formula for the PDF in the textbook. Does involve the gamma function, the formula for the PDF. But there's a typo that should not, on the top there, that should not be capital gamma of little gamma plus 1 all over 2. It should be capital gamma of the fraction little gamma plus 1 over 2. You're supposed to plug the entire fraction little gamma plus 1 over 2 into the gamma function. Kind of a crazy looking PDF. You know, it's hard to predict that would be the right PDF to use. But to tell you the truth, we never really need this, right? Just kind of like with the gamma distribution itself, we never really needed the PDF. I mean, yeah, it's there. It's good to know it's there. And, you know, if you needed it, you could use technology to help you with it, like Mathematica. But mostly we can get by with technology, either calculator, Mathematica, or low technology, the table in the back of the book, to help us deal with the t-distribution without having to worry about the PDF. It is good to know that these t-distribution PDFs do look like bell-shaped curves. They look like normal curves, but they're not. They're not normal curves. they do approach the standard normal curve as the degrees of freedom go to infinity. So as the degrees of freedom get larger and larger, well, here what you see in this picture right here is the t distribution. What gamma 1 is bigger than gamma 2 is, you can see it's skinnier. It's the black one. They're both centered at 0. They both have a mean of 0, but the standard deviation gets smaller and smaller as the degrees of freedom gets larger and larger. And in the limit, as the degrees of freedom goes to infinity, t sub gamma, its PDF approaches the PDF of a standard normal. The book is labeling these graphs with the random variable. In reality, probably would be better to label them with the PDF, but just for short, it's labeling them with the random variable itself. Okay. What are t distributions good for? They're good for more practical confidence intervals to estimate population means when you don't know the population variance, right? Which is pretty much always. Think about it. You're trying to estimate a population mean mu. Why would you know the population variance sigma squared? But that's what we assumed back in chapter 7. Why? Well, because it makes the math simpler. It makes thinking about these ideas simpler to start with. But it's not realistic. So what do we do instead? We use the sample variance, S squared, and the sample standard deviation, S, where in the formula for those things, remember, you divide by n minus 1, which is going to be, hey, that's going to be the degrees of freedom in this situation to create confidence intervals. And something new today, hypothesis testing. And that's why I said this is the most important class for the rest of the semester here, is because if we're getting into hypothesis testing, the big subject of statistics beyond confidence intervals for this course. There are other big subjects in statistics, one of which we'll get to the last week or so of class, linear regression, and others beyond that, multiple linear regression, analysis of variance, it's called ANOVA, lots of other advanced topics that we won't get to, but we do get to in applied stats if you decide you'd like to take that course in the spring. Here's a theorem. Let x1 through xn be a random sample from a normal distribution. Again, these theorems have the assumption that we're sampling from a normal distribution. Why? So that we can actually state them as theorems. So we can actually prove them. They are true in a provable way, a deductive logic kind of way. But remember, in reality, when would you ever be sampling from an exactly normal distribution? Perhaps never. I don't know. Maybe only God knows that answer, the answer to that question as well. Normal enough that you can't tell the difference. That's probably the best way to think of it. A distribution that seems normal, you can't tell the difference. It looks as if it is truly normal. And then, in a sense, you're applying this theorem approximately. But the theorem, as it's stated, you are technically needing to be sampling from a normal distribution with a mean of mu and a variance of sigma squared for the population. Essentially, we're standardizing here, but don't call this Z. It's not a Z. It's not a standard normal. It's a T. It's a T distribution with n minus 1 degrees of freedom, where n is the sample size. Proof of this is fairly short. I don't want to read through it. The essence of the proof is a tricky calculation to ultimately relate this somewhat standardized kind of variable, you might call it, taking x bar, subtracting its mean, dividing by its, well, an approximation to its standard deviation, and relating it to the definition of t distribution through some tricky algebra. Okay, you can check that these are equal. That's the essence of the proof. That probably is how Gossett, in a sense, discovered this by like working backwards. But that would have been really tricky. How would you ever think of taking that and saying it equals that? Like, what kind of motivation would you have for realizing or thinking that would be a good idea? Well, that's, I haven't looked into the history of it, but that's probably what Gossett did. And recognize, hey, that's this. Because this is a z variable up top because I've got a sigma there instead of an s. You got to get the sigma involved. That probably was the motivation, is to get the sigma involved. And Gossett probably also knew that n minus 1 s squared over sigma squared was chi squared with n minus 1 degrees of freedom. That was probably another part of the motivation for this. This, and the notation is not the greatest here. We should really be dividing by this entire thing. This n minus 1 here should cancel with the n minus 1 there. So there really should be like an extra set of parentheses in there. Okay. So this follows a t-distribution, so we can use it. The first place we use it is a formula for a more valid kind of confidence interval in the more common situation when you would not know the population variance. We're pretending there is a population variance, sigma squared, but we just don't know what it is. And again, it's a theorem. To prove it, we need to assume we're sampling from a normal distribution. Then, as usual, our 100 times 1 minus alpha % confidence interval has a similar form as the one back in chapter 7, right? That looks pretty similar. X bar, there's your point estimator, plus or minus a margin of error. That is a special critical value. Now for t instead of z, times a fraction. Before the fraction was s over square root of n, which again was the, think about it with me, that's the standard deviation of the sampling distribution of x bar. Sigma over square root of n, right? Why? If I asked you why, what would you say? There's two reasons you could give. Why is the sampling distribution for x bar, in other words, its distribution, have a standard deviation of sigma over square root of n? There's really two theorems that relate to that in chapter 7. One of them had a, well, actually they both had a name. Nobody? One name started with C, one name started with F. Yeah, actually both start with C, not F. I was thinking of the fingerprint theorem, but that's not relevant. Central limit theorem is one of them. I was also thinking of the cornerstone theorem. So again, the cornerstone theorem, this one tells you when you're sampling from an exactly normal distribution, which is the situation of the theorem in chapter 8 we were just looking at. We can say x bar is exactly normally distributed with mean, mu, and variance sigma squared over n, so therefore standard deviation sigma over square root of n. The central limit theorem, the main difference here is that we're not sampling from a normal distribution, we're sampling from any distribution. X bar is approximately normal with this mean and this variance, therefore standard deviation sigma over square root of n. And this thing is approximately standard normal. So sigma over square root of n is the true standard deviation of the sampling distribution of x bar in this situation. That's not what this is. This is s over square root of n. We're replacing sigma with s. So we don't get a 90, the confidence interval in the case where sigma squared is known, we get something different. And in fact, not only is the point estimator a random variable here, but also so the margin of error is, because s is. S is a random variable. You're going to get different x bars and different s's from sample to sample. But anyway, because you have the s, that's why you need the t, to make it as accurate as possible. What's the best way to interpret what's going on here? Pretend this is 95% confidence so that alpha is 0.05. If we're in the 95% confidence level case, the best way to think about what's going on here is that if you did many, many random samples of size n from the same population, and computed many, many confidence intervals, they'd all be different in all likelihood, not only with different midpoints, but different margins of error in this case. About 95% of them would contain the true population mean mu. We're trying to estimate mu. Okay. So look up T sub alpha over 2. You got to use either the table or your technology. As an example, if degrees of freedom gamma is, say, 13, and alpha, let's say we're doing a 90% confidence level, is 0.1, that would be for 90% confidence. Then we need to look up T sub alpha over 2 is T sub 0.05 with the table. That subscript, remember, by convention means an area to the right of this number T along the axis, an area under the curve to the right. But remember, the table gives you CDF values. Those are areas to the left. So if the subscript's 0.05, I need to look for 0.95 up here. 1 minus alpha over 2. With 13 degrees of freedom, it's 1.771. 1.771. With the calculator, good to practice it both ways. If I go to the distributions menu, I want to use inv t. The normal CDF, TCDF, there's a TCDF, those will give you areas, probabilities, when you know numbers on the axis, T values in this case. Inv t goes the other way around. When you know the area, the probability, they give you the number on the axis. And it's CDF values here, so I want 0.95. Degrees of freedom 13. Paste it. Confirms to be approximately 1.771. We are also going to want to use T distributions for hypothesis testing. Ultimately. But we're not going to do that right away. So here's an introduction to hypothesis testing. That's what we're starting right now. All right, before we get into this problem, what's the big picture? Again, we're doing statistical inference. We've got a sample, a random sample. We want to use the information from the random sample to say something about the wider population. With the confidence interval, it's a fairly simple thing. We're trying to estimate a population parameter, not just with a 1-point estimate, but with an interval estimate where we have a margin of error in such a way that we feel pretty confident, like 95% confident, that the interval captures the true parameter value. With hypothesis testing, we're trying to test theories, you might say, hypotheses. There is something called a null hypothesis that is, well, there's a few different ways to think about it. Sometimes the null hypothesis is thought of as being what was true in the past, you might say, or what's the default assumption that people have. And the alternative is the opposite of that, the alternative hypothesis. Another way to think of that is the alternative hypothesis is your research hypothesis. You think something is true about a population parameter. You think mu, for example, is bigger than something or less than something. let's go ahead and look at this problem to make that real. The mean level of background radiation in the US is 0.3 rem per year. So rem is some measure of radiation. Where does the radiation come from? Lots of sources, okay? It is feared that as a result of the increased use of radioactive materials, this figure has increased. It is feared. Somebody is afraid, and they have this theory that the mean level of background radiation has increased. It's higher than 0.3 rem. That's their working hypothesis. Their research hypothesis is that mu, the true mean level of background radiation, is now bigger than 0.3. That would be what we call the alternative hypothesis. The null hypothesis then would be that it's 0.3 still, or maybe even less. What are we trying to do from that point? We're trying to see if we've got enough statistical evidence from a random sample to say the null hypothesis is definitely false. Or I probably shouldn't have used the word definitely. Probably false. That's even problematic though, because when you say probably, then you're thinking about probability. And we're going to see ultimately there's no way to assess the probability that the null hypothesis is true or false. We are only going to gather statistical evidence against it or in favor of it, you might say, or at least not against it. There's no way to say the probability that the null hypothesis is true or false. That's a common misconception people have when they come out of hypothesis testing, learning about it, is they think somehow it's about estimating the probability that the null hypothesis is true. No, it's not about that. Okay. Part A, set up appropriate null and alternative hypotheses to document this claim. Part B, explain in a practical sense the consequences of making what are called a type 1 and type 2 error. I have not told you what those are yet. Let's do the setup. Again, this is chapter 8, number 22. It's good to write down what the parameter represents. Now, you get points docked if you don't. Not typically, unless for example, on a test, I explicitly ask you to do it. But it is a good practice. Let mu be the true mean, in this case, radiation level. Maybe I should say background radiation level. In the US. In the units of rem. And I'm not sure exactly what rem means, okay? We don't need to worry about it. The hypotheses are, again, the null hypothesis, and the alternative hypothesis. Denoted for shorthand, H0 or H naught, not H naught, but H naught, naught meaning 0. That's the null hypothesis. An alternative hypothesis, our book calls it H1. Other books call it HA for alternative. The alternative, start with the alternative hypothesis. That's the research hypothesis. That's the theory the person who's fearful has, or maybe the people who are fearful have. That mu is higher, it's now higher than 0.3. The null hypothesis technically is just the opposite of that. That mu is less than or equal to 0.3. although we usually write it in what's called a simple form, usually written as just mu equals 0.3. Why? I mean, mu being less than or equal to 0.3 is not the same as mu actually equaling 0.3. Well, for one thing, it's simpler. And in fact, this is called a simple hypothesis when you put an equal sign there. And for another thing, if we can reject the null hypothesis, if we have enough statistical evidence against it, when we assume mu is 0.3, if we have enough evidence against that assumption, like if we get an X bar, an observed sample mean a lot larger than 0.3, if we can reject this null hypothesis, that mu is 0.3 based on that X bar, then we'd certainly be able to reject any smaller value mu as well. Right? If X bar is like 0.8, which in this scale seems to be significantly higher than 0.3, where it's more than double it, that would be strong evidence that mu equals 0.3 is wrong. It would also be strong evidence that mu equals 0.2 is wrong, or 0.1, or 0.175. In fact, it would be stronger evidence against those hypotheses. So it's good enough to just take the boundary value, in this case, mu equals 0.3. It's not wrong in this situation to write less than or equal to, but it's not what's usually done. Okay, and the book does talk about this, by the way. And initially they write it with a less than or equal to or a greater than or equal to. By the way, the fact that this alternative hypothesis is a greater than sign means this particular hypothesis test is called a right-tailed test. A right-tailed test because of the greater than sign in the alternative hypothesis. We're going to end up computing something called a p-value that's going to be an area to the right of something, some number, an area under a curve to the right of some number for a right-tailed test. If the alternative hypothesis had been that mu is less than 0.3 and the null that mu is greater than or equal to 0.3, that would be a left-tailed test, and we'd be computing an area to the left of some number. It all depends on what your theory is. You have to look at the problem statement very carefully to help you understand how to set up your hypotheses as either left-tailed, right-tailed, or there are also two-tailed, where in a two-tailed test, your theory is just that mu has changed. It used to be 0.3, but now it's different, but you don't know which way. How would you write it, the alternative hypothesis for a two-tailed test? You'd put a not equal to sign in the alternative hypothesis, and you'd keep the null definitely in that case an equal sign. That is, if you think about it carefully, probably a bit problematic in a sense, because if you were doing a two-tailed test and the null's mu is 0.3 and the alternative is mu is not 0.3, from a probability standpoint, the chances that the null is true is practically zero, right? Especially if you're dealing with a continuous variable. So why wouldn't you say in a two-tailed test that the null is definitely false and definitely rejected? Because you don't do that. Because we always give the null hypothesis the benefit of the doubt. And this is where the courtroom analogy comes into play. Hypothesis testing is like a courtroom trial. The null hypothesis is on trial. right? And just like when we are trying somebody charged for some crime, just like we give them the assumption of innocence before proven guilty beyond a reasonable doubt, so we give the null hypothesis the benefit of the doubt. We assume it's true and thus proven otherwise. In a sense, we're trying to make it harder on ourselves to reject the null. We might like to reject the null. We might hope we can, because maybe that would confirm our pet theory. And as somebody working for the government or some business here, they're hoping they can prove the background radiation level is higher than 0.3, because maybe that means as a business, they'll get money from the government to help reduce radiation. So they might hope that's true, but technically speaking, to be a valid kind of hypothesis test here, we need to assume the null hypothesis is true until proven, quote unquote, otherwise. When I say proven, I put quote unquote there because it's not really mathematical proof. It's evidence against. And we're looking at the strength of the evidence or the lack of strength of the evidence. So that's the setup and the philosophy behind things, you might say. What's a type 1 or type 2 error? So again, where are we going with this? Ultimately, we're going to take these hypotheses, we're going to do some computations. We're going to compute what are called test statistics and decide whether to, based on those test statistics, whether to reject the null hypothesis or not. Sometimes we'll compute something called a p-value to help us decide. And we will make a decision. Do we reject the null hypothesis or not? No matter what decision we make, we might be making a mistake. We might be making an error. Not a math error, but a decision error. You made the wrong decision. You convicted an innocent person. You let a guilty person go free. You acquitted them. Those are errors, right? Wrong decisions. How do you know if you've made a wrong decision? Well, maybe you don't know, but you could be making an error no matter what decision you make. It's unavoidable. A type 1 error is like convicting an innocent person, rejecting the null when it's true. A type 2 error is like acquitting a guilty person, failing to reject the null when you should have because it's false. The alternative is true. Say that again. Type 1 error, in a sense, in our society, is, in the courtroom at least, is thought of as being worse. You convicted an innocent person, you know, if it's murder or something, to death, death row, or to life in prison, but they're innocent. That would be bad. It's a bad error, type 1 error. Type 2 error is also bad, but we sort of live with it more as a society. Acquitting a guilty person. That could be bad too. I mean, if it's a murderer, then other people could die. But on the overall big scheme of things, we sort of think of convicting an innocent person as being worse than acquitting a guilty person. Of course, we don't want to do either. So type 1 error is when you reject the null, but you should not have because the null is true. Type 2 error is you fail to reject the null. Some people say accept the null. I try to say fail to reject. But you should have rejected it because it's false. So in this particular example, the consequences, the practical sense consequences of making these errors, you got to think about it. Type 1 error means we'd be rejecting this null when we shouldn't have. It's true. We'd be saying the radiation level has gone up when it really hasn't. What are the consequences of that? People will get upset. The government will spend a lot of money when they really didn't need to. People will get scared. They didn't really need to. Type 2 error, what are the practical consequences? Fail to reject the null, accept the null when we should have rejected it. The alternative is true. Radiation levels really have gone up, but we're saying they haven't. So that means now people are going to have a false sense of security. They're going to think they're fine, but they're really not. Measures will not be put in place to reduce the radiation. Maybe more people will die from cancer or whatever than would have been the case if you put mitigation measures in place because you got the funding. Okay, so you got to think about this stuff practically as well and describe reasonable consequences of making those kinds of errors. Can I clarify anything there? These are all really important things. Let's take our 1 minute stretch break. All right, let's start again. Oh, one of these classical long problems here. It is common practice to subject long life items to larger than usual stress so that failure data can be obtained in a short amount of test time. Think light bulbs, right? Light bulbs can last a long time. Actually, I ran across a YouTube video just, I don't know, a month or two ago, talking about how light bulbs definitely can be constructed to last many, many, many years, even over a century. There is a light bulb that is still shining today that is over 100 years old. They showed it. It's in some fire station somewhere. It's lasted that long, okay? I think this might have been a Veritasium video. They design light bulbs to fail, in a sense, because they want you to keep buying more, right? Planned obsolescence. But to test the length of life, you have to subject them to unusual stress. And I mean, I guess with the light bulb, that means more power, though you'd think it'd burn out right away in that case. I don't know exactly. Such tests are called accelerated life tests. Equipment used in computing makes use of metal oxide semiconductors. It's thought that oxide short circuits account for the majority of early failures. Okay, that's a key sentence right there. It is thought. Somebody has a theory. They think something's true. That's going to be probably the alternative hypothesis. The word majority is important as well. Majority. They think it's a majority. You got to be alert for those kind of words. I know in these problems, it's easy to just sort of glance over the first few sentences and not really worry about it too much. But in this case, the key to the problem can be in the first few sentences. And that is a key sentence. It is thought, that majority. If you don't read that sentence carefully and think about it, you'll probably get the wrong answers. To emphasize that, they said, to verify this contention, this theory, to provide evidence for it, A high voltage screen test is applied to a number of circuits and 15 early failures are observed. Let X be the number of failures due to the oxide short circuit. I'm just copying this from the book there. It's kind of an odd way to phrase it. So X is the number of failures in general, but they're also saying 15 early failures are observed. So X was 15 for some particular sample. Part A, set up appropriate null and alternative hypotheses. Part B, if the null is true and P is 0.5, what's the expected number of failures? Okay, let's take these one by one. This is problem 27. What population parameter are we trying to test here? Is it a mean? X is a number of failures. Usually we count number of successes, but with binomial random variables, we could count number of failures as well, effectively treating the failures as if they are successes. The background here is we're really studying some sort of binomial random variable. Oh, now I know what the 15 is referring to. It's not that those 15 failures are due to oxide short circuits. Okay, those are just 15 failures. X is the number due to oxide short circuits. I didn't read it carefully enough. So N is 15, sample size 15. We're really testing the probability of quote unquote success, which in this case is failure. I mean, if I'm describing that, I probably should say failure. Let P equal the probability of failure due to oxide short circuits. Okay. Success means the failure was due to oxide short circuits. Now, again, I'm defining the parameter here, which in general is definitely a good thing. And on a test, I might ask you to do it, though. And on homework, sometimes they might ask you to do it. But sometimes we just skip the step just to save time. But technically, it's an important step to define what your parameter is. That can be thought of as a probability. It also could be thought of as a proportion. The proportion of all failures that are due to oxide short circuits in the long run over many, many, many of these semiconductors. All of them that are manufactured by your company, for example. So you could call it a proportion as well. We're testing, think of it either as a population probability or a population proportion in the long run. People think of it both ways. Remember that the theory is the majority are due to oxide short circuits. So the alternative hypothesis, that's your theory, is that P is bigger than what? The word majority is important there. .5, yeah. The null hypothesis H0 and the alternative hypothesis H1, or you can write HA, it's fine. Write down the alternative first. It's that P is bigger than 0.5. The null technically is the opposite of that. though it will not be wrong if you just write equals. People usually write equals. And in fact, I will usually write equals. I'm just not doing it here initially to emphasize that technically speaking, the null is the opposite of the alternative. And so technically speaking, it's less than or equal to. Once again, we have a greater than sign. So this is once again a right-tailed test. Here we actually will be ultimately finding an area to the right of something under some curve or some discrete histogram in this case. That's part A. We did it. Set up appropriate null and alternative hypotheses. Part B, if the null is true and P is this boundary value 0.5, so they're talking about the simple hypothesis, this one. What is the expected number of failures due to oxide short circuits in 15 trials? Should be able to reason that out in your head. P really is 0.5, N is 15, you would expect what? It's not a whole number. What? 7.5, 7.5 failures. This is A here. B, expected value of X, oops, sorry, is N times P, right? Binomial, mean. 15 times 0.5, if P is 0.5, like the null hypothesis in simple form will assume, which is 7.5. Okay. Taking it step by step here, part C, let us agree to reject the null in favor of the alternative if I typed these PowerPoints like 15 years ago. And I wrote a greater than or equal sign as equal greater than sign. I got the beta in there this way, but I didn't typeset this very well. If X is greater than or equal to 11, in this way, we are presetting alpha to what level? What is alpha? I haven't said. We're agreeing to reject the null, to say we think the null is false, and the alternative is true, if we get a test statistic, you might call it, X, number of failures for a sample of size 15, to be 11 or 12 or 13 or 14 or 15, greater than or equal to 11. That is a relatively large value of X, because it's a right-tailed test, that if you think about it intuitively, if the null is true, those numbers, 11, 12, 13, and 14, and 15, are far enough away from 7.5 to the right that seems to be evidence against the truth of the null hypothesis. You know, many of your homework problems, even to this point, you've had questions that said something like, would you be surprised if so many things happened? They were setting you up for this kind of problem. We're trying to find the probability of rejecting the null if the null is true in a sense. In this case, the probability that X is greater than or equal to 11, and that is what alpha is. It's the probability of rejecting the null in favor of the alternative if we assume the null is true, that P truly is 0.5. We're making an error. Part C is all about making an error in the final question of it. That's what alpha is. It's the probability of making a type 1 error. That's what I'm trying to say. alpha by definition, the symbol alpha in this context represents the probability of making a type 1 error, meaning the probability that you reject the null when you assume the null is true. We can write this as a conditional probability. To be more specific for this problem, that means the probability that x is greater than or equal to 11 when p is actually 0.5. That's a binomial probability calculation. And I can use my calculator. I can write it this way. I mean, we don't usually write these things as conditional probabilities. I'm doing this essentially for emphasis because I'm assuming p is 0.5. Usually we would just write p less, the probability that x is less than or equal to 10 here. And we just know in the background in our minds that p is 0.5. 1 minus of the distributions menu, binomial CDF, trials is 15, p is 0.5. That's what I'm assuming. Hey, this is where I'm giving the null hypothesis the benefit of the doubt. I'm assuming it's true for the sake of this calculation to figure out the probability of a type 1 error. And the x value here, when I write it this way, is 10, not 11. X is discrete here. We're usually going to do hypothesis testing with continuous variables. And so then I'd want to put the 11 there. But this one happens to be discrete, and so I want to put a 10 there. I already did the 1 minus, so this is about 0.059. And why don't we go ahead and just round that to 0.06. So the answer to the question is I'm presetting alpha, the probability of a type 1 error, to be about 6%. Think about this, okay? So you're testing these conductors and 15 of them to failure. The null is that p is 0.5, but your theory is that it's bigger than 0.5. Before you actually do the test, remember probabilities are before the fact. What are the chances you'll make a type 1 error? What are the chances that you will incorrectly reject the null when you should not have because it's true? It's about 6% based on this setup, based on your choice of agreeing to reject the null when x is greater than or equal to 11. That was a choice. Could have made a different choice. Could have chosen to reject the null when x is greater than or equal to 12. What would have happened if I had done that? That would have been a 12 there. That would have been 11 there. This would have been a bigger probability that we're subtracting, and this would have been a smaller number. Smaller alpha, smaller probability of a type 1 error. So if you make your rejection region, your critical region that has both names, in this case, x is greater than or equal to 11, that leads to rejecting the null when x is observed to be 11, 12, 13, 14, or 15. It's also called a critical region. Both names are used. It's somewhat arbitrary. Yeah, it's up to you. You're choosing here 11 or greater. But if you choose a more extreme critical region, 12 or greater, you'll be less likely to make a type 1 error. That sounds good, right? Less likely to make a type 1 error, but guess what? There's a trade-off. If you make the probability of a type 1 error smaller, you make the probability of a type 2 error greater. You can't have it both ways. Oh, can't have your cake and eat it too. Or can you? Can you make both probabilities small? Yes, you can. Partially, the probability of a type 2 error is not really well defined because you have to assume the parameter takes on a specific alternative value rather than a generic bigger than 0.5 value. And partially, you can also make the most small if you make the sample size bigger. That's one other way to make it both smaller. But you still need to be careful in choosing this rejection or critical region. Part D says find beta if P is 0.6, if P is 0.7, if P is 0.8, if P is 0.9. What's beta? Beta is the probability of a type 2 error. Hey, beta comes after alpha in the Greek alphabet. Alpha, beta, gamma, delta, epsilon mixed up. Alpha is the probability of type 1 error. Beta is the probability of a type 2 error. But it's not well defined. We say it is the probability of a type 2 error, but that's an ambiguous statement. Because in order to calculate beta, you have to assume P is something particular in the alternative hypothesis. And if you pick different things for P there, you're going to get different answers for beta. So it's not a well-defined thing. Which brings up a question. If it's not well-defined, then how is it useful? I'll talk about that. Just hang on. I'm not going to do all 4 of them. Let's just do one of them. You know, once you can do one, you can do the others pretty quickly because the setup is the same. Beta is the probability of a type 2 error. That's the probability that you fail to reject the null. Some people say accept the null, but you know, prosecuting attorneys never think they're wrong. They still think that defendant is guilty, even though the defendant was acquitted. I'm using hyperbole here, by the way, in saying they never think they're wrong. They never think they're wrong. They think that defendant's guilty, even if they failed to convict them, even if they're acquitted. So they don't say the defendant is innocent. They say I just failed to convict them. I still think they're guilty, but I just failed to convict them. I didn't have enough evidence against them. Fail to reject the null when the null is true, or null is false, excuse me. Null is false. In other words, H1 is true. That failing to reject the null means you're not in the rejection region. You're not in the critical region. In this example, X is less than 11. And since this is discrete with whole number values, that's equivalent to X is less than or equal to 10. Given in the first case, P is 0.6. But the book, again, also asks you to do P is 0.7, P is 0.8. Maybe we should do one more besides P is 0.6. It's coming from the rejection region, which was just described in part C. We agree to reject the null when X is greater than or equal to 11. That's the arbitrary choice again. I mean, it's arbitrary, but it is somewhat logical because it did make alpha fairly small. So use your binomial CDF again. Still 15 trials, but now P is 0.6. There's still a 10 here. I'm not going to do a 1 minus this time. Just doing that. Answer is about 0.783. Yeah, whoa, boy, that's a pretty high chance of making a type 2 error, isn't it? Maybe we should do a different beta calculation. Maybe we should assume P is 0.7 instead. It should be smaller, right? If P is higher. Because the expected value is going to get higher and higher if P is higher. If I assume P is 0.7 instead of 0.6, X is still 10. This one, yeah, this is smaller, 0.48 5. So again, which one's right? They're both right, depending on what P is. But wait a minute. We don't know what P is. Post is useful. We're doing a bunch of theoretical calculations, but we don't even know what P is. People still do these calculations because what they end up doing is they end up deciding before the fact what extreme value of P, in this case above the null value, they want to be able to detect with high probability and low probability of a type 2 error. They decide ahead of time which P they're going to calculate here based on what is a big enough difference from the null hypothesis to make it an important difference. You know, if P is just barely bigger than the null, 0.501 or something instead of 0.5, yeah, that's bigger than 0.5, but it's so close to 0.5, why do you care? But if P is 0.8, 80% are from the oxide failures or whatever it was. That's significantly higher than 0.5 and enough that I'd like to be able to detect that if it's true. So maybe you decide you want to do the calculation here when P is 0.8. Well, let's go ahead and do it. And if that's really small, then you're happy. And it was a calculation worth doing. How small is it? Well, reasonably small, 16%. This leads to something called the power of the test. And what is the power of the test? The power of the test is the probability of a correctly rejecting the null when you should, because it's false. That's power, doing what you want to do as a prosecuting attorney, convicting that person who is guilty. But wait a minute. We'd again have to think about different alternative values. And it's really the opposite of the beta. Beta is the probability of failing to reject the null when you should have because it's false. Power is the probability of rejecting the null when it's false. Accurately rejecting the null when it's false. Power is 1 minus beta, the power of the test. For these different possible alternative values, so it's not well defined until you pick a particular alternative value. Just like you want beta to be small, you want the power to be high. Well, that makes sense. Power is 1 minus beta. And again, you do that for different situations. I think, yes, this problem does ask you for that, but we're not going to take the time to actually do it. Running a little short on time here. Part F, if we observe 12 early failures that are due to oxide short circuits, should H0 be rejected? The answer would be yes, because 12 is in the rejection region. And because we rejected, we are subject to a type 1 error, not a type 2 error. If you reject the null, maybe you made a type 1 error, maybe you didn't, but you didn't make a type 2 error. If you fail to reject the null, maybe you made a type 2 error or you didn't, but you did not make a type 1 error, right? If you convict, maybe you convicted an innocent person or a guilty person, but you did not acquit a guilty person. Did I say that right? If you convict, maybe you convicted an innocent person or a guilty person, but you did not acquit a guilty person. If you acquit a guilty person, maybe, or if you acquit, you either acquitted a guilty person or an innocent person, but you did not convict an innocent person. You can't make both type 1 and type 2 errors in a given problem. They might ask, what are the consequences of making a type 1 error? Here, you think there's more due to oxide short circuits than there really are. If you observe 10, you're not going to reject, and you're subject to a type 2 error. All right, last few minutes here, just looking at number 31, which is one of the problems I'm assigning. Whenever a motorist encounters braking problems, the villain is always held to be the brake pad. trace elements, especially titanium, can combine with other elements to form minute particles of titanium carbon nitride, which alter the degree of friction and lead to unequal wear. The percentage of titanium in brake pads should not be bigger than 5%. Studies conducted to detect a situation in which the mean percentage exceeds 5%. All right, so that it's trying to detect if it exceeds. So this is right tail. So far, we've always looked at right tail tests. It's strange to think of percentages as being means. Usually we think of percentages as being proportions, but they want you to think of it as a mean here. They do have the word mean in here somewhere. I thought I read it. The mean percentage, yeah. It's right in the middle here. And if you look further down in the problem, you see an X bar. So we are talking about a mean. Also notice before we look at parts A through C here, that this is called significance testing instead of hypothesis testing. Huh? Why is it called significance testing? It's because it's a different way of thinking about hypothesis testing. It's still going to be hypothesis testing. We're just calling it something different. Part A, we're still going to have a null and alternative hypothesis. The null would be, well, mu will be your mean percentage of what? Mean percentage of titanium in brake pads. Yeah, that's it. Mean percentage. By weight, I don't know. The alternative hypothesis is that it exceeds 5%, that mu is bigger than, say, 0.05. And the null would be that it's less than or equal to 0.505, but go ahead and write it as equals, unless told otherwise. Maybe for the first few problems, you should write the less than or equal to. So that's the setup. Discuss practical consequences of making a type 1 and type 2 error. If you reject the null that it's equal to 0.05 in favor of the alternative, you're saying it's higher than 0.05 when it's really not. And you're saying titanium is more of a problem than maybe it really is. And type 2 error is failing to reject them when you should, and you think titanium is not a problem when it really is. Part B says, or part C says, a sample of 100 brake pads yields a mean percentage of X bar. Notice that's an X bar, not a mu. That's a sample statistic. 0.051, just barely bigger than 0.05. And they're assuming you've got a population standard deviation that's known, sigma. It says find the p-value of the test and decide whether H0 should be rejected. Notice they're not giving you a critical region here. No rejection region. That's what makes this, in part, a significance test. There's no given rejection region. Instead, they want you to find something called a p-value. That's another reason we call it a significance test. Give me 30 seconds here. What is a p-value? I guess I'm not going to have the time to write it down. A p-value is a probability. First of all, p, probability. Of course, there's many words in this class that start with p. Population, proportion, percentage, probability, parameter. P-value here is a probability. It's a probability of observing a test statistic, in this case, little x bar, as extreme or more extreme as what you actually observed under the assumption that the null hypothesis is true. Write it, say it again. A p-value, I will put the video up, share it with you. You can rewrite this very last part of class. P-value is the probability of observing a test statistic as extreme or more extreme. In this case, bigger than or equal to 0.051. When you assume mu is really 0.05. And to compute the p-value, in this case, you have to convert to a z, standard normal, by subtracting 0.05 and dividing by sigma over square root of n. Use the z table or use normal CDF in your technology. And if the p-value is pretty small, like for example, less than 0.05, then you'd probably reject. And if it's not super small, then fail to reject. How small is 0.05 the answer? It is a common answer people use, but it's not set in stone. It is somewhat arbitrary for smallness of p-value. All right. Have a good day and weekend ahead.